Today, we will cover how you can design an AI agent with a multi-agent, hierarchical design, using the RAG pattern, and advanced techniques like RAG, memory, and human-in-the-loop to make it more robust. This is a RAG loop, which stands for reason and act. The agent receives a task, then it reasons, what tool do I need? And then it acts by selecting that tool. This loop repeats until it can finally generate a response. Now let's design our system. We'll use a case study, an intelligent note-taking agent. Let's define its core requirements. First, it needs multimodal input. It must take text, audio, and images and automatically transcribe, classify, and format them. Second, intelligence. It must answer questions about our notes using Agentic RAG and take proactive actions like create PDF notes. Third, personalization. The agent must learn our preferences over time. And fourth, maintenance and analysis. It should answer meta questions and use human-in-the-loop to ask before deleting duplicates. These 4 requirements will define our agent's architecture. To build this system effectively, we'll adhere to a few core design pillars. First, loosely coupled. We will build a system with independent, loosely coupled components. Second, highly extensible. System supports easy, non-disruptive addition-removal of agents' tools. Third, modular. Follow modular design with reusable, distinct components. Fourth, accuracy and reliability. We will prioritize high accuracy and minimize hallucinations. And fifth, resilience and speed. Prioritize resilience, graceful failure handling, and quick response. We'll use a 3-tier architecture. First, the perception tier, which handles input. Second, the planning agent, which decides what to do. And third, the execution agents, which perform the tasks. We will model our AI workflow as a graph. This is highly extensible and easy to visualize. Each node in the graph will execute a piece of logic, and in our design, a node can be an agent itself. We are using a multi-agent approach because it allows us to divide our complex system logically. Each agent will have a single responsibility. Our agent roster includes the security agent, presentation agent, ingestion agent, retrieval agent, communication agent, analysis agent, and maintenance agent. At the top, the presentation agent handles all user interaction. The request is first passed to a security agent to check for prompt injection or PII. It's then forwarded to the task planner agent. This is the brain that breaks the task down and routes it to the correct execution agents, which are grouped by their function. Finally, all agents are connected to a shared memory database, allowing them to share state and context. A critical part of our design is the persistent state. This is the shared context, the memory of the current conversation that all agents can read from and write to. This state object holds everything for the current request, like the user's input, their preferences, the chat history, and the current plan. Crucially, it also tracks the agent's response. Since agents might run in parallel, we can't let them just overwrite this field. To prevent race conditions, we use a reducer. This ensures that new data is appended to the dictionary, rather than replacing it, keeping all parallel updates. It also holds execution logs, the final response, and a thread ID, which acts as the unique request ID for the entire conversation. This shared state is the single source of truth that allows all our independent agents to work together. The task planner agent is the master planner. We'll model its logic as a graph. It starts at the reason node, calling a powerful LLM to create a plan, or DAG. The plan is a list of steps. The planner then moves to the act node, which executes the current step by calling a tool or another agent. If the plan is not finished, it loops, continuing to the act node to run the next step. Once all steps are finished, it moves to the reduce node to synthesize a final answer and then ends. Next is the ingestion agent, a critical component that processes all incoming data. We can map its logic as a graph, showing how data flows from input to storage. Internally, it maintains a state object that tracks the data as it's transformed. It starts at the input node, which acts as the orchestrator, receiving files, URLs, or text, and routing the data to the correct processor, like OCR for images, a scraper for URLs, or a transcriber for audio. All processed data then flows to the text classifier, which uses an LLM to determine what the text is, for example, a CS note or event. The task is then split. The formatter node handles semantic chunking, preparing the data for the vector database. The summarizer node creates a concise summary. And the metadata extractor uses techniques like NER to pull out a title and relevant tags. Finally, all three outputs are saved by the data store node to a vector DB and a metadata DB, completing the pipeline. The retrieval agent is responsible for finding and synthesizing information using a pattern called Agentic RAG. Here is its internal RAG loop, which stands for reason and act. Like the other agents, it also maintains an internal state to track its progress. First, the plan query node reasons, using an LLM to formulate a precise search query. Next, the execute retrieval node acts, calling a tool to search the vector database. Then, the evaluate node reasons about the results. Are these documents good enough? This is the agentic part of Agentic RAG. If the documents aren't good, it decides to re-query, looping back to the planner to refine the search. This loop continues until the agent is satisfied. Once satisfied, it finishes and moves to the synthesize answer node. Here, it uses an LLM, grounded on the retrieved documents, to build the final, comprehensive answer. This is the communication agent. Its job is to handle all I/O with the outside world, like sending emails or writing files. Internally, it runs a reason act synthesize flow. And just like the others, it uses a state object to pass data between steps. First, the reason task node analyzes the goal. Am I sending an email or creating a PDF? It then sets the correct tool and arguments in the state. Next, the execute tool node acts. This node uses the Model Context Protocol, or MCP. This means one act node can access a context of many different tools, like sending an email, writing to the file system, or generating a PDF. If a tool fails, it can loop back to the reason node to retry. Once successful, the format response node synthesizes the tool's raw output into a clean, final dictionary. So far, we've designed the major components of our AI agent: a core graph-based workflow, a task planner, and specialized agents for ingestion, retrieval, and communication. But to make this system truly robust, we need to cover 3 more critical areas. Subscribe, and in Part 2, we'll dive into human-in-the-loop for data hygiene, security agents to prevent attacks, and advanced token optimization to keep it fast and affordable. Subscribe for Part 2.